Okay, so then I'd like to go on to how we implement the solution to the wave equation numerically, how we code the solution to the wave equation. And again, it's like the heat equation and like Laplace's equation. We turn the partial differential equation into a difference equation. So here we're going to turn the wave equation, partial differential equation, into a difference equation, just like we did for heat equation, just like we did for Laplace's equation. And so that's what I do on this slide, basically. So we're going to divide space and time up from being continuous, like it is in the partial differential equation, to being discrete. So a discrete time would divide the length of the string up into discrete steps, and would divide the time evolution up into discrete steps. And to do that, we need to introduce the size of the steps in space and the size of the steps in time. And so I'm going to use this notation that we used from the last class, and I think we used some of it from the first class on partial differential equations. So my steps in space are going to be, the spacing in space is going to be A, the steps in time, the spacing in time is going to be H. So I've got to now rewrite the second order partial differential with respect to time as a difference equation. I got to rewrite the second order partial differential with respect to space as a difference equation. At this point, right, we've met now how to do this for first order differentials and how to do this for second order differentials. We've met the fact that we can appeal to Taylor expansion to rewrite these differentials in terms of difference equations. We've met the fact that if you've got a first order differential equation, that's really an equation for the slope. And so your difference equation is one that it approximates the slope. And if you've got a second order differential equation, it's one for the curvature, the rate of change of the slope. And so your corresponding difference equation is one that approximates the curvature. And so in this case, we've got two second order differential equations with respect to space and time. And so these are the difference equations that approximate the curvature in space and time. So just a couple of comments on here. So the one for the time differential, obviously see H as in the denominator, because we're talking about the time evolution. And we see in the numerator here, right, the value of the function at some time t and at some time one step earlier, minus h, and one step later, plus h. And that's going to give us the curvature. And the same thing over here for the spatial differential, right? We see a squared in the denominator, because that's the time, the spacing, the space step. And then in the numerator, we see the values of the function at some coordinate x and at a coordinate to the left and right, plus or minus a. That's how we're going to get the curvature. And so that sort of physically how we replace the second order differentials with these difference equations. When I plug them in to the wave equation, so I plug the second order time differential in downstairs here on the left, second order space differential downstairs over here on the right, we get this little equation here. And remember that there's the velocity of the wave is sort of a coefficient of proportionality between the space and time dependencies, or space and time second order differentials. So we see that velocity squared downstairs here. And so this is how we built our difference equation corresponding to the partial differential equation. This is how we're going to solve the partial differential equation. So on this slide, all I did was rearrange that difference equation that popped out of the partial differential equation for the value of the function at some particular coordinate x, space coordinate x, at some particular time in the future, so t plus h. And it's written in terms of, by rearranging the equation on the prior slide, it's rewritten as this little expression here. If you look through this, what do we see? We see the value of the function at earlier times, so t, and t here, and t here, and t here. We also see it at an even earlier time, t minus h, because that difference equation from the prior slide had the function at time t, and it had the function at a time t plus h later, and a t plus h and a t minus h earlier. So that's something that's new. We also see for the to calculate the value of the function at position x, it involves the value of the function at an earlier time at position x, but also the value of the function to the left and right of that coordinate x, so at plus a and minus a. So we see those, the value of the function at this later time at a certain coordinate is determined by the values at earlier times and at different locations, at neighboring locations. This plot kind of shows that more clearly. So if you look at this plot, this is discrete space and time. Horizontally is at discrete space points. So this is from the left to the right, is from one end of the string to the other end of the string. And from upstairs to downstairs is from early times to later times. So we're trying to calculate the value of the function that corresponds to the wave on the string at this particular location, I, and at this particular time, j plus 1. And what this little picture is showing you is that it's a function of the values of the functions at this earlier time and this even earlier time. And it's a value, it's dependent on the values of the functions at the same x coordinate here and the neighboring x coordinates as well. And so all that is in the right-hand side of this equation here. You also see this parameter, right, which involves the size of our space lattice, the size of our time lattice, and the speed of the wave that depended on the tension and the mass of the string. There's a little bit of a subtlety for the implementing code in the wave equation that didn't come up for implementing or coding Laplace's equation or heat equation. And it's related to how you deal with the initial conditions. And it's related to the fact that to calculate the value of the function at the next step in the future, you have to look back to not only to the current step, but the step before that. You have to look back further in history. So that means that there's a subtlety with your initial condition, right? That equation for the value of the function at the next time step. So imagine you've got your initial condition and you want to step to that first time step. Well, at that point, you're going to look back and say, what is the function at the previous time step? That was the initial condition. What is the function of the time step before that? We don't have that. So the way this is often handled is that on that very first step in your calculation, your code is kind of going to be sort of special. It's a special case of your code. When you look back at the prior step, you're going to say that prior step and the step before that you don't really know about, they had the same values. Thereafter, you always got 2 steps behind you. You can always look back 2 steps and calculate according to this differential equation. But you've got to deal with that initial condition in a special way for the wave equation. So that's what I tried to describe here. You see, I've written down 2 equations, upstairs here and downstairs here, for the value of the function at this later time in the future, when we've taken that step into the future. The lower equation is the one that we met on the last slide. It's the one that we derived from the difference equation. The upper equation here is the special one that we're going to use for the first step. And it's the one that's saying, well, let's just assume that function before the initial condition was exactly the same as the initial condition. What it changes is this first term or pair of terms in the difference equation. So in the full equation, look, you have 2 times the value of the function at time t minus 1 times the value of the function at t minus h. If we assume that on that very first step, if this guy here, the value of the function at t minus h is just the same as the value of the function at t, then this is like 2y minus y, which is just this piece here. So that's all that's done. It's sort of like the assumption that, so it's an important point. It's like the assumption that the string was released from rest. So we are building that string being released from rest into our solution here. One last point that I wanted to make is that, so the first part of this applies to the Placid's equation, heat equation, and wave equation, right? In all of those cases, there are going to be what we call approximation errors when we figure out the solutions. So we're approximating a partial differential using Taylor expansion as a difference equation. So that difference equation is an approximation of the original partial differential equation. And you could imagine, right, depending on how fine your discrete space, your discrete time is, that will determine how accurate your calculation is going to be. So you might imagine that, well, look, if I want an accurate solution, I just make the spatial lattice and the time lattice really, really fine. And then I'll get an accurate solution. So that is true for the heat equation. The heat equation kind of works that way. It's actually not true for the wave equation. So with the heat equation, when we have the glass window or when we have the steel rod immersed in water, right? Heat flows in the heat equation. Temperatures change in the heat equation until you get to some sort of steady state. And that turns out to lead to a stable difference equation solution. As long as you pick a fine enough grid in space and time, your solution to the heat equation will be the stable, steady state solution of the steel rod dropped in the water bath or the window pane between the hot indoors and the cold outdoors. That's not true in the wave equation solution that we're going to work with. See, the wave equation is kind of like this perpetual motion machine. So you plug the string, you unleash this wave. That's in our wave equation. That's not going to some sort of steady state where eventually the string comes to rest. We've not built that into our wave equation. Rather, that wave is just going to be propagating up and down the string. So it's going to go on forever. That means that sooner or later, approximation errors due to the fineness or the coarseness of the space-time grid are going to start to distort your numerical calculation. And in the end, they will overwhelm your numerical calculation and you'll just see noise in your solution. So this time when we solved the wave equation numerically on our space-time grid, if we look at early times, then we'll see the wave propagating along the string. But if we were to wait long enough, eventually that we would lose that wave into the approximation errors, the approximation noise for this problem. And it's because there's no equivalent of the heat equation where you have eventually reached a steady state. In this case, there is no steady state. Our wave equation, the wave can never die off.